Welcome to Science, Scripture, and Reason. I'm Julie Thomas, and I'm filling in for our usual host, Randy Anderson. He's out of town. Tonight, we are taking a look at planetary habitable zones. You may have heard stories about finding life on other planets or water on other planets. All the planets that scientists have found, are there any that we could live on someday? To explore these possibilities, our speaker tonight is Dr. Brandon Reddell. He currently works at the NASA Johnson Space Center in the Engineering Directorate. He has degrees in physics from the University of Texas, an MS in applied space physics from Johns Hopkins University, and a PhD in physics, high energy space physics, from the University of Houston. Currently in his work, he supports all of the human spaceflight programs in the area of ionizing radiation effects produced by the galactic cosmic radiation, solar particle events, and the trapped radiation belts around the Earth. Dr. Reddell also serves as an adjunct professor in astronomy at Los Angeles Pacific University and occasionally in physics and astronomy at the University of Houston at Clear Lake. And additionally, he is an adjunct professor in the School of Divinity at Regent University, where he teaches cosmology and astronomy design in the universe. He's active in his church and a strong advocate for showing how the results of science support the Christian worldview. Dr. Reddell, it's an honor to have you, and we'll turn it over to you.
All righty. Well, thanks, Julie. And it's a pleasure to be back here. I think I've spoken to this crowd pre-COVID, maybe. It's good to be back. I think tonight, let me share my screen here, but while I'm bringing it up, um, I do work in engineering, but I'm a physicist, and in my day job, I spend a lot of time working with all these new programs, right? The lunar programs, the low Earth orbit programs, and so forth. I help designers basically build their system so that they can withstand the natural radiation environment, right? And so Julie mentioned galactic cosmic radiation. You probably heard of the Van Allen belts and things like that. And so I'd be happy to take at the end of the talk. I can address basic questions there. I would say I'm not speaking tonight as a formal scientist on planetary habitability, but I've been an astronomer, an amateur astronomer for 35 years, right? Ever since I've been in middle school, and that's really what motivated me to go into science. And uh, in particular, I put together a series of talks, and so this is sort of a revamp of a talk I did to our RTB chapter in Houston, maybe definitely before the COVID years. I think it's 2017-ish. And so I thought it'd be good to bring it up. It's really part of a series of talks that really want or aim to show, just how unique Earth is and our position in the universe. And so that obviously leads to questions about, are we special or not, right? And so there's bigger implications here, but for tonight, I really just want to show, um, you know, there's habitability means a lot of things, and so I just want to make sure you understand that, so you're prepared when you see news, that you kind of fully understand it. I do think it's getting better in the sense of how they report. Um, like in published literature, how they now talk about it, but as short as 5 years ago, you'll see here in a few minutes how there was almost false advertisement in some of these things, and within the science community, in particular the Royal Astronomical Journal, right? Shortly after some of these articles that came out, there were many scientists that were sort of outraged in the sense of promoting other positions that weren't necessarily supported by the observations or even the data. And so I think a lot of that's starting to be corrected, right? I don't think there's an agenda out there, but people are anxious, right, to find, ET life or whatever. So anyways, tonight's really more just a review of habitable zones, plural, right? There's more than just one. And so the outline of my talk is as follows. as I've kind of just been mentioning about false advertising, I want to show you some headlines from an article, from a discovery from several different articles. This is actually still pre-COVID, um, but it's not really too far off in time, right? So it's certainly relevant to today in some of the articles we see. I want to review habitable zone definitions just to make sure we're all on the same page, and then a little bit about main sequence stars, because these planets are around other stars. And so I just want to get some terminology down and our bearing straight at what we're looking for. And then I have a lot of data. So I don't know if you've seen the charts, but I'm not going to go through these in gory detail, but I'll try to hit these at a high level. But these are known habitable zones, right? So every one of these need to be in place if we want to find life like we have it here on Earth, for instance. But it also has implications for any uh, biological life. And then, real quick, I want to show you at the end some exoplanet catalogs that you can go and peruse and look at the latest findings yourself. And if you're into this sort of thing, you can do searches. And I think on one of them, you can actually download the database and categorize the data yourself and start looking into it. As far as the talk, I think because there's so much data, I'm okay if you want to interrupt, if you have questions, because there are a lot of topics. Otherwise, waiting to the end is fine too. So either way is okay with me. And like I mentioned earlier, if there's any generic questions about what NASA is doing these days, I'm also happy to, at least on the human spaceflight side, willing to talk to you about that as well. So, uh, as you see here, this is the headline article for a space.com article. Now, this was 2015. Kepler is a space telescope that's looking for exoplanets. And here we go. Closest Earth twin in pictures, right? Kepler 452b. That was a lot of times they identify these planets with numbers. And so they show this picture here, right? Now, this looks a lot like maybe if we're talking about Earth's twin, we would expect something like this, right? We have rivers and lakes. Now, obviously, this is a drawing, but this is what they're publishing, all right, at this discovery, right? Where there's rivers and lakes. We see volcanic activity in the background. We have a nice sunlight, yellowish star, pretty blue skies with atmosphere, nice large moon, and mountains, presumably, from plate tectonic activity and so forth. So we're just in the even now, even though 2015, right, 10 years ago, we're still at it, just at the tip of the iceberg. We have no way of seeing these kind of features right now, right? We're hoping James Webb Telescope can help us find like certain signatures in the atmospheres, right? But right now we have no way to even determine if there's magnetic fields on the planets, for instance, or in some cases, in most cases, even if there's a moon, right? So we don't have our technology is nowhere close to doing something like that. Furthermore, with this particular announcement, here's just a few quotes from various articles. I'm not going to read all of these, but some of them are kind of funny. NASA just found Earth 2.0, right? There was a period of time they kept using 2.0, right? We see that in a lot of software things these days, or new versions of something, right? They call it a 2.0 version, right? Like this is literally an Earth 2.0. Bad news for God, right? I mean, all the problems have been solved. And so um, the general idea is, what are they hinting at when you see these type of articles, right? There is some bias on implications. Now, from a science perspective, there is legitimate science going on, and it has nothing to do with sort of the background that's being hinted through these titles here. Even though there's some people that might believe that, but there is legitimate science, because the more we learn about planets, exoplanets, right, that's solidifying our knowledge in planetary formation. It helps us learn more about our own solar system and the origins of Earth and so forth. But in general, I mean, it's probably safe to say that humanity, right? We do have a fascination. I mean, just look at all the movies from Hollywood about ET and um, there's many people thinking, if there is ET life, right, that it's got to be more advanced if we're especially if it's been visiting Earth, right? They've been able to travel here, right? If that's the case. And so maybe they have a lot of answers that will help humanity out, right? So there's this general plea, also, um, you know, better medicines, better technology, what have you. But that's sort of the general idea, right? There is a plea for help from beyond, right? And so all this to say, there's a general interest and then there's a scientific interest. Now, as far as definitions, you may have heard habitable zone in its most general term, and honestly, that's still even today. When they say something's in the habitable zone, they just mean you're at the right distance from a star where you can have liquid water on the planet, right? James Casting's a atmospheric scientist who specializes in exoplanets. He's at I think Penn State University, and so he's kind of coined with this primary definition since 1993. And then some of his colleagues, Koparapu, in 2013. So I have a lot of data in this presentation from some of these papers. They've kind of updated the idea of what habitable zone means. And so the second definition here is really more closer to what it's considered as today, and that is the circumstellar region around a star, right, for a planet, right? So meaning the right distance from a range of distances from a star that has a carbon dioxide, water, nitrogen-based atmosphere that can sustain liquid water on its surface, right? And so we say there's a range because there's other factors that determine if you can have liquid water on the planet. And then I'm going to talk a little bit about runaway greenhouse, right? If we're basically it's the distance where the surface water is evaporated, right? If we're too close to the star, right? It's kind of like the Goldilocks zone, right? If you're too close, it burns off, and if you're too far away, you freeze. And so, and then finally, actually on the bottom there, um, part of my Zoom's blocking this. Let me move it here. Okay. Yeah, on the bottom here, the other thing you need to understand is something called the continuously habitable zone, CHZ. Sometimes you hear that referred to. And if you think about it, over the history of a star, right? Like like stars have their own life cycles. And so in general, stars, just like our sun, gets brighter and brighter over time, all the way up until its end of days, right? And um, as it's getting brighter, it's putting off more energy, and so planets receive more energy, and so that affects the conditions of say liquid water or these other ones that I'm going to talk about tonight, right? And so that evolves over time as a function of the star life cycle, right? The lifetime, and so that's also need to be understood because if it really took life, let's say, earliest life on Earth, is from cellular life about 3.8 billion years ago from the fossil record, right? So the sun's increased in brightness at least 20% more um, from over the last 3.8 billion years. So that's a huge amount of energy, and so somehow the planet needs to compensate for that. Now, next chart here is so this is a review. I'm not sure how many of you are familiar with astronomy, but let's look at the graph first. Okay, so this is and you can find these on Google. There's various versions of these, right? And they're in every astronomy textbook. This is called a Hertzsprung-Russell diagram. It's just named after the two gentlemen who noticed when you plot temperature of a star versus something called luminosity, which is basically its energy output, right? You see all the stars clumped together in certain areas. So this diagonal line kind of going through the center, this is called the main sequence. I don't know if you can see my cursor, but I'm going from the top left, at a 45-degree angle all the way down, right? It starts with, on the top left, you have the highest luminosity, which is your vertical axis. Now, on this graph, temperature is moving, it's getting hotter as you go from the right to the left. And it's plotted reverse so that you can have the sequence, and when you're drawing stellar, like how they come off the main sequence, right? When a star becomes a red giant and a white dwarf, right? It's just easier to draw the tracks when they plot it this way. But the bottom is temperature. So hot temperature is on the left. It's the blue stars, and then the red are the coolest stars. And so luminosity is often referenced. So astronomy has big units, right? And so it's often easier to put things in terms of like the sun, for instance. So a luminosity of one means the same luminosity as our sun, right? One times the sun, right? So a 10 would mean 10 times more luminous, right? It produces 10 times more energy. And so the biggest stars are the hottest. They have the higher core temperatures. They burn nuclear fuel faster. Therefore, they have the shortest lifetimes, but they're the hottest and brightest. And so you come all the way down. If you go to the luminosity of one, move over here, you'll see our sun right here, and go straight down, right? It's a G star. You may have heard that our sun's a G2 type star. Each one of these stellar classifications, there's really 10 subdivisions, but they're basically tell you what type of temperature the surface of the star is, and then its luminosity. And then there's other interesting information too, but for the purposes of this talk, it's really identifies the temperature and luminosity. Now,
Hey,
um, is
Brandon,
there a question?
yeah, I got a question. Can you hear me?
Yes, sir.
Okay, so my question is, how do they measure I can understand how they could measure the luminosity because that's just the brightness, but how do you measure the temperature? You can't.
Yeah, so stars are very hot objects. So they're called black bodies, right? They're perfect absorbers and emitters. So they emit energy, right, in all frequencies. Now there's spectral emission lines and absorption lines and things like that, which tell you a little bit about the chemistry of the stars. But overall, they can measure the spectrum, and every hot object follows this. Actually, Max Planck is a famous scientist who studied temperature and quantum mechanics and things like that. And so it forms a black body curve, and there's a nice theoretical formula for that. And so if you can measure your black body curve, the peak of that curve is directly proportional to the temperature. And so all they do is you just need a spectrograph and you measure the spectrum at all frequencies, and you can get the temperature.
Second question, does the star move along that line or is it stay there at that?
Yeah, that's a great question. So it does not move on the line. So for instance, are you able to see my cursor?
Yes.
Okay, so here's the sun, right? So our sun is about halfway through the life of its age, right? So it's got maybe 5 billion more years, right? I don't know if you can see the it says 10 to the 10 years, right? 10 billion years, right? That's the estimate life of our sun. And that's approximate, but it's around there, right? So we're about halfway through there, right? The Earth's 4.5 billion years. The sun, formed basically at the same time, just a little bit before. So what happens is at the end of its life, because of the mass of the star, like our sun, right? It's not a big mass star, so it's not going to blow up like a supernova. It's going to swell up and it's going to move off the line into this giant phase. And so as it's trying to, it starts after it burns up all of its hydrogen, right? It tries to burn the helium and fuse helium and so forth. And there's not enough. So eventually it'll kind of bounce around here and then it'll go to this super giant phase. And then once it burns all of its hydrogen and helium, it won't be able to fuse anything else. And so what happens is it'll quickly drop down and it'll become a white dwarf. And from there, all the white dwarfs that we know today, they have a predicted lifetime of like 30 something billion years or something, right? So way longer than the universe is old, right? So will the end fate of our star is a red giant, right? Which will impact life on Earth, right? Life will not be able to survive that on Earth because it'll swell up so big that there's actually a lot of study to understand just will it actually come all the way out to Earth's orbit or really close to it. But either way, it would kill all life on Earth. But it'll end up as a white dwarf and just cool down over billions and billions and billions of years. So yeah, all stars that these graphs like white dwarfs and giants and supergiants for any star that's not on the main sequence, that means it's in a dying phase. Now, what's not shown here is when they first uh when a and I'm going to talk about this when we get to the astrosphere habitable zone. When a star forms from an interstellar dust cloud condensing, right, gravity pulling all this material together, and when it gets compact enough and generates heat where nuclear fusion can kick off, um, they're a little bit off the main sequence, and they once they get stabilized, right, they'll fit somewhere depending on its mass, right? They'll fit on this main sequence, and so that's where a star spends about 90% of its time. Uh, also, and 90% of the stars we see out there, right? If you go out in a dark sky site, 90% of the stars you're looking at are in their main burning phase, um, hydrogen burning phase, and so that's where you get on the main sequence. I do want to point out the lower right are the red dwarfs. You might heard of stars called red dwarfs and M dwarfs. Right, M is the classification, and dwarf means they're much smaller than our sun, therefore they're cooler, and therefore they have a lot longer lifetimes. So you see here it says 10 to the 11th year, so that's 100 billion years, right? So so these can last quite a while, but there's a lot of issues with these stars, and I'm going to talk a little bit more about these. But I guess instead of reading like all this text here, really the point of this is just to kind of show you, most of the stars are M dwarfs all the way up to G stars, and then you get fewer and fewer as you get to these higher mass stars. And so if we're going to look for exoplanets, we want to be looking at like F, G, K, and M, right? And I'll show you throughout this presentation, especially near the end, all the exoplanets we're finding are, around F, G, K, and M stars. Did I answer your question or any other questions?
Yes, thank you. I never
Okay.
quite understood that before. Now I do.
Oh, okay. That's good. So again,
Oh, we get another question.
okay.
Yeah, come on up here. Hear you better.
Are there actually places in the universe where there's enough dust gathering together to form a star?
Yes. Yeah.
Found places like that?
Yeah. They're in
Groceries?
even in our galaxy. I mean, I do a lot of astrophotography, and you can go out and look at any nice spiral galaxy, and if you take a long enough exposure, you'll see they call those star formation regions. You may have seen some of the recent James Webb Telescope images. Sometimes there's a feature called it's called the Eagle Nebula, but inside there, they call it the fingers of God, right? And they're little gas clouds that are literally there's stars forming in those clouds, and they got pictures of them forming. The Pleiades, right? The little near Taurus, that little small, looks like a little mini Big Dipper, right? Those are all brand new stars, and so yeah, we see them all over the place in galaxies. You just need a thick dust cloud and something to kick it off to, like another star moving by it will cause it to collapse, and then once you have that happening, gravity takes over, and then it doesn't happen like instantly, right? It happens over like tens of thousands of hundreds of millions of years, depending on how big the cloud is. So hopefully that answered the question. Now, what I'm showing here, again, using the great source of Wikipedia. Now this is legit though. This is just showing a little bit more detail of those stellar classifications. So when I say stellar, I'm talking about other stars, not our sun, right? It's just referring to another star. So again, you have the hot stars on the top row all the way down to the cool stars. And so this is the temperature range of the stars, basically, the color type. If you go to the fourth column, right, it tells you, right, the temperature in the really, if you know the temperature, that tells you a lot about sort of the radius of the star, like how big it is, right, and its mass. And so there's relationships, but they can estimate the mass and the size. And so as you can see, for O type stars, right, the smallest ones are 16 times the mass of our sun, but they're most of them are way bigger than that. They can be 1,000 times. And then, but what I want to show you, pay attention here to the last column on the right. Fraction of all main sequence stars. So I already told you, if you just randomly select all the stars you can see, 90% of those are on the main sequence, right? So it's most of the stars, right? Now, of those main sequences, 76% of those are M dwarfs, right? Only 7% are G-type stars like our sun. And then when you get a little bit higher mass and, hotter temperatures, right? F, A, B, O, right? They're 3%, 0.6, 0.1, right? So they quickly drop off. So there's not many of those. So because of that, as I was mentioning in the last chart, right, this talk's really in the focus of exoplanets, right, is really looking for planets around these type of stars, F, G, K, and M. But pay attention, M dwarfs are by far the majority, and we should expect to see most planets around these type of stars. Now, going back to habitability now. So I'm going to talk about 9 quote unquote habitable zones. Now, for further information, I think many of you may be familiar with Reasons to Believe. Hugh Ross is an astronomer, and he wrote a nice book called I'm drawing a blank now. The Improbable Planet. Really referring to Earth and the fascination with trying to find other planets. And the question is, should we expect to find a lot out there, right? Surely, I mean, there's trillions of stars right out there, with each, it's well known now there's probably planets around every star, so surely there must be tons of life out there. And so why aren't we seeing this and finding this? So it's tied to this idea of habitability. So on each one of these topics, now I'm going to cover these kind of lightly. At the end, I'll show you the references. And so you go look at this yourself and look at, even though I pulled some of this from Hugh Ross's book, I went to the actual papers to pick up some of this information. Now, the general habitable zone, the traditional, right, liquid water. So, and since 1993, so I have here, so casting back in 1993, he had a one-dimensional sort of radiative cooling model where you're looking at the energy input from the sun and then certain atmospheric processes, what's taken place with an assumption of the type of atmosphere, right? And you just vary the distance, and that'll tell you when you get liquid water, right? If you can maintain it. And so the general range for most of the last few decades, the habitable zone ranged from 0.84 astronomical units. Okay, so that 1 astronomical unit is just the distance from here to the sun. So that's like 93 million miles or something like that, right? So 85% of that distance, right, would be, you had to be at least that far away from it. If you're too close into there, you would evaporate your atmosphere. And then on the far side of it, it extended out to 1.67 astronomical units. Now, I said this is a cutout from the actual paper from Koparapu 2013. So around the mid 2010s, they went to a much better type of modeling. You know, science improves. They had better atmospheric models, and they went to not just trying to maintain temperature, but you'll see in some of the other references to in some of the other charts that they were looking at stellar flux, right? How much energy is coming into the play as opposed to just the trying to maintain a temperature. And so they adjusted the inner habitable zone, especially, right, to 0.97 astronomical units. And so so the current, you know, up until kind of around this time, right, there might be some updates to this, but the newest updated numbers around these values here. So here's a nice graphical picture of that. And so again, this is just plotted. If the vertical axis is the star temperature, right? It's effective temperature, right? So our sun has a temperature around 5,800 degrees Kelvin.
Well, question time.
Okay, sorry, we
Sure.
it just took a while for the picture to update on Zoom, apparently.
Oh, okay. Do you see it now?
Yeah, we do now.
Okay.
I do have a question on the previous picture. Was the previous slide, it was 0.97 astronomical units. Does that mean if it was less than that, you're gonna have a runaway
Yes.
greenhouse? What does
Yes.
that mean?
Yeah, that's exactly what it means.
So we're only just 3% different than what we are now,
But yeah, if
right?
so that would, well, actually, so this is where it gets tricky, right? If you're only considering distances where you have liquid water on the sun, I mean on the planet Earth, yeah, if you got any
Yeah.
closer towards the sun, only 3%, right? We would start this evaporating our oceans, potentially the atmosphere eventually. You know, the closer you get into the sun, the quicker it would burn off. But that's the implication. And
Okay.
actually, if you on this next chart, there's a graphical representation of that. So this is from the same paper. So hopefully it's updated. Here's just a graphical representation of that table. Again, we have more stars out there. So yeah, these are stars at the time of this publication, but there's definitely a lot more. But the point is if you look at this blue circle, hopefully where my cursor is, where it says habitable zone in the green section right here on the left side, you know, our sun's around 5,800 degree Kelvin surface temperature, and the ratio of 1. That means if you take any star that has the same stellar flux as our sun and divide it by the stellar flux of the sun, right? So this is just normalizing it to our sun, right? So Earth fits right here. And so this is what we mean by 97 percent or AU. We're just inside the habitable zone on that feature alone. Now there's some more updates that I'm going to get to, but yeah, that implication alone says we're just barely inside the habitable zone. And so Venus you know, is way out here. So because it's closer to the sun, right, it has a lot more energy hitting it, and so it moves up on the scale to the left here, and so that's why it's out here. And then Mars would be way out here on the backside. Early Mars is just if you read the paper, it's just referring to you know, people are trying to consider, you know, when early in the solar system formation, if Mars had water, it would have started out about at this location. So remember, this was based on this one-dimensional model. And so at this time, now there could be some more updates, so just keep that in mind. But around the mid 2000s to 2020, right? This 1D model is still widely used. And the reality is life's, three-dimensional models are better, but they're more complicated. So, and I'm going to show you some results from a 3D model. Here's another way of looking at it in the context of all the exoplanets found to date at that time, right? 2013. You see this so again, this is the plot on the same scale on the bottom, right? It's just the star's effective flux relative to the sun, right? So a 1 means this is the same output as the sun. And then you had, in terms of mass of planets, right? So you look at all these circles up here, right? Even back then, all these planets are all just too massive, which makes sense, right? We're going to see the biggest planets first, uh, as we're developing our technology. But if you start looking in and around, right, they're starting to find a few that are in this gray box here. And so what the gray box is basically telling you, Earth's just inside the habitable zone. It's not in the ideal location, which is the darker gray. But at the time, this is kind of what they were thinking. Mars, right? Remember, Mars is smaller. It's smaller than the Earth, right? So it has less mass. That's why it's down lower, and because it's further away, it's receiving less energy than the sun. So it has less of a ratio, and that's why it's off the graph here. And so, a lot of people are looking at life on Europa, right? It's a water world around moon. It's a moon around Jupiter that's frozen. It's way over here somewhere. Now, this alone doesn't mean you can't just have life, right? Potentially you could, but just for liquid water, these are some of the relative results. Now, what else do we need for habitability? Well, all stars send off energy. You may have heard on the news, and I deal with this all the time in my day job, is there's outbursts of the star, right, that send out like we see the aurora borealis, right? When the sun's very active, it sends a lot of energy. It interacts with Earth's magnetic field. Um, there's a lot of ultraviolet radiation, right? I mean, nowadays, like even me, I have to worry about getting sunburned all the time because there's so much UV light. That's not good right? Life needs a little bit for cellular processes, DNA, cellular at the cellular level to work. But if you have too much, it's not good. And so in this particular paper, this is the only one I could find at the time also. So remember, they focused here on M, K, and F stars, right? It doesn't make sense to do this for any of the short-lived stars because they're just too short of a lifetime. But what you're seeing here, these graphs are basically the same. So let's look at the left one first, right? It says start. This means at the start of remember I talked about the continuous habitable zone, right? This is where they would line up at the beginning of the star's life, and then the right graph would be towards the end. And what it's showing is the vertical axis is basically the distance in astronomical units. It's logarithmic, but either way, it's just think of it as distance, and the bottom's mass. The green band here is the liquid water habitable zone. Okay, so these guys in this paper looked at how much UV light the planet is receiving given how close it is to the star, right? And you needed just the right amount required for life processes. And so depending on the mass of the star and its location, you get this purple band. So just looking where these two overlap, you only have a small region here. And then over the course of the life of the star, right, it gets more luminosity as it grows up in the habitable zones. These two habitable zones expand, but there's still an overlap, right? So it evolves over time a little bit. But the point is what they concluded in this paper was that for water habitable zones, they need to be there has to be an overlap with the UV habitable zones for solar-like stars, and what they mean by that are just stars close to the G-type star, right? So that would include F and K stars. And then what they found though is for the M-type stars, these don't overlap for these type of stars. So what you don't know, and I haven't talked about yet, M stars are very active stars. They're 100 to 1,000 times more active, meaning there's a lot more flares coming off. And so basically that purple curve would be a lot higher, right? So it would never overlap this green zone. So yeah, I'll talk a little bit more about M dwarf stars, but also remember when I was showing the stellar classifications, remember M dwarf stars are 70%, make up 3/4 of the main sequence stars. So in other words, 76% of our stars don't have overlapping water and UV habitable zones. So that kind of takes out a lot of stars right off the bat, right off the this idea of, hey, every star might have a habitable zone. So just other things to consider.
Hey,
Now-
Brandon, I got another- Hey,
Question?
Brandon, I got another question. Why does the mass of the star, okay, so this is, the x-axis is the mass of the star, right?
Yes.
Is right? Yeah. So why does the mass of a star have anything to do with the UV habitable zone?
Yeah, because the mass of the star determines. Let me go back here for a second. Some of these plots, I don't think I picked one here, but you see here, you see where I say the lifetime of the star is proportional to 1 divided by the mass to this 2.5 power. Okay, so in other words, the mass of the star basically determines the core temperature, which is where you're having the nuclear fusion happening. And so that dictates how long the lifetime of the star is, but it also dictates how hot it gets and the type of processes happening on a star. And so there's a lot of other complicated factors involved in that, but the short answer is that the mass of the star really determines how active it is. If that makes sense. So
Okay, yeah,
if
okay,
it's a
I'm
very
starting to see
active
it.
star, it's got a
Yeah.
lot more UV outbursts.
Okay, and the reason why UV is important is because you have too much of it, that's a bad thing, it breaks down chemistry. Is that
Yeah,
the reason?
yeah, exactly. So for every one of these, it's the idea is there's a sweet spot, right? We're talking about habitable zones, right? We talk about liquid water, right? If you're too close, you burn off your water. If you're too far, it freezes. UV, right? If you're too close, you
Yeah.
get too much of it, and it's bad for DNA. But if you're too far of it, you don't get just the right amount that's needed to help start up life when they're like I'm not talking about this in the paper, but you can go into the resources. Life requires a little bit of UV light for and I'm going to talk a little bit about this on the next chart or the next habitable zone. But yeah, both for photosynthesis and DNA life, you need a little bit of certain amounts of UV light to kick it off, right? It helps energize cellular functions. So it's like a Goldilocks zone.
Got it.
So
Yeah, what's the resolution on water? I know I understand the habitable zone where you can have liquid water, but how closely can we determine if there is liquid water and how much in the atmosphere or on the surface?
well, that's a tricky process. Yeah, I would say, it would depend, right? So that's actually an active area, right? Is because I'm going to talk about this here in a few minutes. There's a lot of things that affect the amount of cloud coverage, right? And so the type of atmosphere, the rotation rate, and all these things determine other features of the atmosphere that might retain water in an atmospheric sense versus liquid water, right? And so there's a lot of factors in play here. So let me cover these other ones and see if that helps. It's not going to really define a resolution, but it will tell you that, hey, this is pretty complicated. A lot of factors in play here. So I know that's probably not a great answer, but there's more to talk about on that. Now, closely related to,
Good.
so was there another question?
Nope, we're good.
Nope.
Okay. Now, UV light is really, I kind of look at it, it's, there's a couple factors here, and I actually left off, I kind of hint at it here on the bottom right, on this chart. I'm leaving off extreme space weather conditions, but I wrote an article that was on the RTB website, and it was based off a couple papers published in mainstream astronomical journals. And since then, I've seen at least 4 or 5 that look at, when you look at M dwarfs, we know that they're very active storms. Like I said, they're 100 to 1,000 times more active than our sun as far as UV outbursts, right? Like X-ray flares and things like that. There's a lot of studies that show for M dwarf stars, all the planets are really close, and I'll explain that here in a little while. But they're so close, and when you have an active star that's 1,000 times, right? It basically, on very short time scales, can remove planetary atmospheres. And so in a sense, that's really another quote unquote habitable zone. But I'm not talking about that in this presentation. But UV can be broken into, there's the life DNA effect as well. It has to overlap with the water zone. But then you also have to consider, again, relative to Earth, all life on Earth depends on photosynthesis. And so too much UV is bad for photosynthesis, but now photosynthesis requires a lot of other processes. Here, I took this from Hugh Ross's book, but there's a lot of papers he references in the back. I was flipping through just the other day, I found this article, and I don't think it's on the version I sent you, Jim. But this is the only thing I think I changed differently. I just added this reference here if anyone's interested, because there's a lot of study going on right now with understanding how the concentration of carbon dioxide determines if photosynthesis can work or not. And so that's related to how much UV energy you're receiving, in addition to some of these other ideas here. Along this idea of photosynthetic life, in this particular paper, they looked at, so if you remember, the earliest bacterial life shows up as soon as it can on Earth at about 3.8 billion years, right after the late bombardment period. So the Earth's been cooling down, and cellular life just shows up, right? So it's a big question of how that actually happens. So what you see here in this plot here is just, and this is a relative response to sort of today, the incident radiation from the sun today versus that's what this, I don't know if you can see my cursor, but where it says a radiation from the sun, that solid line underneath of it, right? That's kind of like that's how much radiation is coming off the sun, let's say. The high bolded red curve is basically our early Earth atmosphere, the response of radiation at ground level, like 3.5 billion years ago, right? 4 to 3.5 billion years ago. And then this green over here is present day. So and then by the way, this dotted line here is what our present day would look like if we had no ozone. So this bottom label here is talking about the wavelength of light. So as you see with this blue arrow, if you move to the left, it's more energetic, right? Smaller wavelength means more energetic. You may, when you look for UV protection, right, there's a UV ABC, right? Those are just different band levels to the left of this green curve here, or kind of overlapping it a little bit. But the point is, the early Earth atmosphere wasn't well developed, and so this paper estimates. I don't think I put it on here, but it's like 1,000 up to 1,000 times more. You can just look at this graph, right? This red curve's a lot higher, and this is a logarithmic scale. It's hundreds of times to 1,000 times more UV exposure uh, in the early days, and so that was bad for DNA life, but for the implications for photosynthetic life, right? This affects how much CO2 is in the atmosphere, and so this paper kind of talks a little bit about it, but you really need to look into that other link I just showed. Let me back up here. This paper is really good at explaining. Basically, these authors, this particular author says that with it's a mystery how life even started, even photosynthetic life, because of the levels of CO2 would have prevented that in the early days. So it's sort of a big question of how did life start on that just by looking at the photosynthetic zone. So that's kind of tied to UV, and then the third part of that. So this is sort of still tied to UV, but we looked at you need a certain amount for DNA to work, like life permitting DNA and cellular processes to work. You need it affects a certain amount of conditions that are separate from the DNA, but combined with other effects affect how photosynthesis works. And then we have what we're familiar with, like ozone, right? A planet needs ozone to help shield, not only protect people and life on Earth, but crops and so forth. And so what I'm trying to show here, if you don't know what ozone is, right, it's chemically it's O3, 3 oxygen atoms. The way it's produced in the atmosphere, right, we have a decent amount of oxygen in our atmosphere, and when UV light from our sun hits the upper atmosphere, right, it breaks apart the O2 and the 2 oxygens, and then they recombine with each O combines with another O2 and it forms ozone. And this is all happening in our upper atmosphere, right? So you need a planet that has oxygen in order to produce ozone. And so I'll flip back to that other chart here in a second, but this is sort of a graphical illustration of our Earth's atmosphere. So all the ozone's up here, just in the bottom part of the stratosphere. Now, ozone, it's number one, it absorbs 97 to 99% of the UV short wavelength light, right? If I go back to this plot, right, short wavelength, here's the green curve for present day. So we're talking about, around 300 and less, right, is more energetic. If you get way down here, you're getting close to X-rays and gamma rays. But this is still all UV or ultra high UV. Ozone shields all that out and helps protect life, right? That's what this red curve, this dotted curve is right here, right? If we had no ozone, all this UV light would be able to reach the ground, which would be very, very bad for life. And that I don't think I put it on here, but again, when you're looking for like sunscreen protection or shirt, right there, or your eyeglasses, right? There's UVA and B, and I think there's a C band, right? So these are all in these categories here. But what's important relative to this talk is, so for life, as we kind of mentioned, backing up kind of in a summary, right? You have a star producing all this energy, It also, part of that energy is UV light. That depends on the star's mass and age, right? That was what that one question is. That determines its luminosity, which is how much energy is coming off the star. You need a certain distance to the star, which has to overlap with water zone and a couple features of UV, right? So you need the right combinations that allow DNA and cellular processes to work. You need the right distance for photosynthetic processes to work. And then you also need a planet that has oxygen that can produce ozone. And so you may be wondering, well, what happens if you don't have ozone? If you look at the bottom left there, too much ozone. And this particular paper talked about, basically at ground level, if you had 10% of the amount that's up in the stratosphere, if you had it down on ground level, like I think you're in Sacramento, is that right?
Yeah.
Yeah, so like I don't know, I know
Yeah.
like in Houston, I'm in the
Yeah.
Houston area, and I know LA, like in the summer now, we'll get like ozone days, right? Ozone alerts. I don't know if you get them in Sacramento, but when you get a lot of just bad weather conditions, really hot atmospheric conditions, you can get a high ozone concentration on the ground, and a lot of people, it affects their health and breathing and stuff. So that's the effects
Yeah,
that
it's getting worse here
it's getting worse. Is that what you said?
yes,
Yeah.
every
Yeah.
year
So
it
like,
gets worse.
yeah, exactly. And so that's that's kind of a feature as our and it's tied to climate control, climatology and stuff like that, right? So but the point is if you have too much ozone on the ground, not only is it just bad for people, you get smog, right? And then that also causes problems for respiration and crop yields, and I mean there's all sorts of effects. So which are needed for life.
Yeah. Hey, Brandon, Chuck has a question for you.
Just
Sure.
I'm clear on photosynthesis. Photosynthesis was the main producer of oxygen.
No,
I mean, is
well,
that where most of the
yeah,
oxygen?
well, no, yeah, yeah. So one, I'm not really talking about it here, but yeah, when you look over the course of history of the Earth, right, the oxygen concentration was very low for the first 3 billion years. So and most of the life, like all of the life, was like algae and bacteria, and that basically through photosynthesis, right, it releases oxygen, and that's how the Earth's atmosphere got built up, predominantly.
Oh, okay.
So yeah, no photosynthesis,
Okay.
you wouldn't have the oxygen, which later on, if you're going to have an advanced life form there that can survive, where you potentially need ozone, at least as we know it on Earth. I mean, you might not need it for, you can make the argument, hey, well, there could be a life form that could live without ozone or with ozone. Now that's possible, but we're talking about life as we know it because this is all we know. Um, if we're looking for Earth 2.0, right, these are the things we got to consider. But as you're seeing, there's more than just liquid water is needed. If you think about it, radiation from the sun is not good for any, like, I don't know of a single, it's so deleterious, right? When we use it to kill cancer cells, right? We have to protect astronauts in space from too much radiation, right? It's bad stuff. And UV light is a type of radiation that's really bad. It's not good. We know too much of it kills any kind of DNA signature, right? So it's not good for any kind of life. Okay, let's see much. Am I doing okay on time? I'll try to speed it up here.
Yeah, I don't know how much more, so you probably need to try to, half an hour.
Okay, yeah, I'll do these last few pretty quick. So other things, planetary rotation rate. So our Earth spins around. Now, this picture on the right is just kind of a schematic showing how, clouds help reflect light, some of the radiation, but also the stuff that comes through, right, heats up the surface and not only heats it up, but some of it gets reflected back. Like this time of year, like right now, this week was really bad in Houston because it's been really hot and it gets cloudy every night here. So all that radiation coming off the ground at night bounces off the atmosphere and it gets trapped. So, it's like 80 degrees in the morning here. It's miserable because of cloud coverage. So the reflection is called albedo. You may have heard that term. But in this paper, now this is kind of what modernization of these models is starting to look at. They're starting to look at, well, hey, we know a planet may have land and water. They have different heat capacities, right? So depending on the rotation rate, the percentage of water versus the percentage of land, it's going to absorb heat differently in different locations, so that how fast it rotates basically determines how much the planet heats up. And so what they found by going to a three-dimensional model and considering a fast rotating planet, like Earth is considered fast. Slower ones, like slower rotation rate would be a slow one, right? And so that where it says this green line here and the blue line, that was the inner and outer habitable zone that I showed earlier. Now, when you look at the inner zone, that's what these dotted lines are. This far one over here, this orange curve, right? So that's the 3D inner zone for a very slowly rotating planet. And then for an Earth-like planet, they're saying, hey, this inner zone is really closer in, and so that puts Earth now, you see, a lot deeper into the habitable zone. Right, with the 1D model, we're right on the edge, but when you start to factor in rotation rate, we're a lot more comfortably inside this habitable zone. That's ultimately what this is showing. So that's a factor, right? Basically, you have stellar temperatures here based on the star type, right? And so that would determine, basically the more rapidly the rotating planet is, right? It generates different kind of cloud bands, affects the albedo, and so the faster it's going, basically, it pushes all these zones further out. So that has to be considered. And then tied to that, right, we have seasons on Earth, right? That's due to the tilt of our axis, right? Even though we're spinning like a top as we go around the sun, right? And like in the winter time in the US, we're tilted in such a way that even though we might be a little bit closer to the sun, we're further. The tilt's actually like this. We're away from the sun compared to the summer where we're tilted closer to it, right? And so this particular paper just looked at, hey, what about the tilt? Because we know even in our own solar system, not all the planets have this 23.5-degree tilt. Well, what happens is from their studies on this graph here on the lower right, when you look at, this is watts per meter squared, right? So it's basically how much power, energy being absorbed in the planet as a function of latitude on the planet. And you can see it quickly goes for planets at higher inclination, you get a lot higher average temperatures. And so that determines, right, the ability for water on the surface. It also affects the atmosphere in such a way that it can have influence on the location of the UV habitable zone and all the ones that come with it, the photosynthetic and the ozone. So the basic idea here is the higher the obliquity, the further these zones get pushed out as well. And then three more, tidal zone. So you guys have heard of the tides, right? It's just the gravity tugging on Earth. So, the Earth's spinning, any liquid water, as it spins fast, it wants to kind of get squished a little bit. And then when you have the moon is a lot closer than the sun, so it's tugging in one direction that's closest to the moon, and then you have the sun tugging So you have the neap tide and uh, the lunar tide and solar tides right there. It's all depends on the configuration, but the point is that a tidal force is when you, let's say you're looking at the tidal force between the Earth and the Moon, right? It's just the difference of the tug, the gravitational force on the near side of the Moon versus the far side, right? And that's called a tidal force, and that affects things on Earth. Now, the reason why we care about it for habitability, there's a few papers on this, and this is very important. Um, the so I think you all know when you go out and look at the moon, we always see the same face of the moon facing the Earth, right? Um, Even though the moon's rotating, it does one rotation at the exact same time it takes to go one full revolution around the Earth. So that's why we always see one face. That condition is called a tidally locked position, right? We always see the same face. And that happens when you get too, like when the moon's too close to the sun or to the Earth. Likewise, for exoplanets, especially those around M dwarf stars, right? 76% of the stars, right? They're going to be tidally locked. Their orbital rates, to give you an idea, relative to our solar system, like our whole solar system would fit inside the orbit of Mercury relative to our sun. And that's how close they would have to be to an M dwarf star, right? Because they're such low mass. And so that forces them to be in a tidally locked position. And so that's a big deal because when you have one side facing the star, it's going to heat up quite a bit compared to the dark side, right? And so that affects circulation if there is an atmosphere. If it survived, it will affect planetary atmospheres. The tidal forces being that close, you can imagine just the amount of volcanic or the geological forces usually causing like volcanic type activities. And then it also, I have a note here in the second bullet here. If there's any obliquity, right, tilt to the planet, which affects your seasons, the tidal forces cause that to erode as well. So you can't maintain seasons at all over long periods of time needed for life to survive. A couple other major conclusions from some other papers that had come out that basically this paper by Heller in 2011, right? He said for Earth-like obliquities, right? If we're talking about like Earth 2.0 type planets, for stars, it says Earth-like obliquities of planets in the habitable zone around stars with a quarter of the mass of the sun, right? They're eroded in 100 million years. So you remember a quarter of the mass of the sun, it puts it down in the M dwarf state. Again, we're talking about 76% of the stars, right? So if life needs billions of years, this is a problem for a timing situation for life to sort of take that long to get to an advanced state, right? So that's what I'm trying to say here. They also concluded planets that are about 90% the mass of the sun, the tilt takes about 1 billion years to erode, or over 1 billion years. So it allows for enough time for planets to remain in the other habitable zone. So yeah, these are just sort of trades, right? It all depends on the mass and how close it is to the star. So keep in mind, tidal zones, you have a lot of volcanism and heating and circulation problems. So there's a lot of issues. And then finally, there's the last two here. Then these are sort of more astrophysical in nature. There's something called the astrosphere. another term you may have heard of is called the heliosphere, right? Think of the influence of our sun, right? The solar winds going out into our galaxy or into our solar system. At some point, there's a boundary out where you're in interstellar space, right? And that's called the heliopause. Now, if you remember, I think in 2012 or so, I think it's 2012, like Voyager's actually passed through the heliopause. So it's technically in interstellar space now, both Voyager 1 and Voyager 2. Here's another picture on the left. If you think of our sun, and this is not to scale, but if you think of our sun shooting off a solar storm and it hits our magnetic field around the Earth, it gets deflected around that. Just that's called the magnetopause. And the space around inside there is called the magnetosphere. So analogously to that, we have the heliopause and the astrosphere. And so the whole point of this idea is people have done studies that look at the interstellar. We talked about star formation early on. Somebody had asked about that, right? All stars form from the from interstellar clouds condensing. And so most molecular clouds are where star clusters are formed from. They have a density of about 100 to 1,000,000 atoms per cubic centimeter. I know there's a lot of data, but they have a known density. And so what happens is these are from this paper. I encourage you to go look at it. But the short of it is, if you think about it, there's a trade-off, right? Too much or too little, it's not good for life on Earth. And so in this case, we have our sun or any star, right? Depending on its mass and energy, it's pushing out all this energy and it's pushing away, it's keeping that interstellar cloud from pushing in into the habitable zone, right? So there's a balance between how hard the star can push out against the interstellar cloud. But if it's too weak, then the interstellar cloud can condense all the way into the habitable zone, and in which case planets that are in this habitable zone are exposed to more deadly sort of interstellar type radiation. So there has to just to be just the right amount of interplay between the stellar winds and the density of the molecular clouds that are nearby. And so this particular paper basically said, for stars that are like our sun, they estimated that you'd have conditions where the astrosphere could collapse into the habitable zone, basically, giving us a lot of radiation. Those events could happen every 1 to 10 billion years. And so for stars a little bit smaller, right, it's less frequently. And so this puts constraints on how big the stars can be, like going the other direction. So this is more complicated, but the point is there's a nice balance between how strong the star is sitting out at stellar winds versus the molecular density around it, right? There has to be a balance there. And then this is the last one. This was in 2016. There was a probe around Venus, and they actually discovered something that many people didn't know about, but it was theorized. And so what you have is, if you have a planet, so that's what this big circle here is, a planet. The sun is on the right, pushing, the starlight, the stellar winds are going from right to left. And so what happens is there's something called an ambipolar electric field that's created, and how that's created is light from the star can dissociate the electrons from the atoms. Electrons are very light particles, so they get picked up in the stellar winds and they get pushed off, and so the ions are a little bit heavier, so they get dragged behind. And so because of that, you get an electric field built up that helps basically accelerate the rest of the ions out of the atmosphere. So it accelerates atmospheric loss. And so the type of atmosphere you have and how close it is to the star determines how fast that happens. And that gets to this idea of, well, there's a lot of papers studying how, how close you can be to the star and how quick it can basically remove an atmosphere from a star. And so, again, if 76% of the stars are M dwarfs, many of those planets are very close to the star. And so not only do you have the tidal effects, now you have atmospheric loss, you have a lot of UV problems, temperature problems, right? Maintaining liquid water and so forth. So you get all these things that start stacking up. And then I just want to conclude here, and I can take some questions. I encourage you, there's two big databases out here. One's at it's the University of Puerto Rico, right? This used to be the Arecibo kind of site. They have a Habitable Worlds database, and then the NASA ones maintained at Caltech. I actually took this snapshot the other day, right on May 7th. We have 5,893 planets, quote unquote, confirmed. Now you can actually, if you go into this website, you can actually download it into Excel and you can start to play with these parameters and do some filtering. But I just wanted to show you on their homepage on the Puerto Rico site, this is their top candidates for stars, for exoplanets, for habitability. They define this parameter called Earth Similarity Index on the far right. So, if it's a 1.0, it means it's just like Earth. And it's based on a bunch of parameters. But these are the ones that have the highest quote unquote similarity. But what do you notice here for the type of stars? Like all these planets, just about every one of these is around a M star. There's a couple K stars in here. So they're saying that even though all these are Earth similarities, it makes you wonder, given all those topics that we just discussed in the last hour, how similar is that really when we know for M dwarf stars we have a lot of major issues, and there's quite a few number of papers that have been published to talk about, like I said, planetary atmospheres being gone, high solar activity, and so forth. And so,
Brandon, I got a question.
yeah, I'm pretty much done. So yeah, I can take some questions.
Okay, so my question just is the very first one even in there, that's 90.97. Is that that's just the planet? They don't take into account the star or anything else?
Right.
And- okay.
Yeah, there's actually, I don't remember off the top of my head. I'd have to go on this website. Yeah, they tell you the factors that go into creating that number.
I don't see anything that's not an M. Oh, I guess there's a couple Ks in there.
Yeah, that's what I'm saying. Like this is oops. Yeah, so they have a list, literally just go to this website, you can see the list unless they changed it in the last 7 days. But when I updated this presentation, I had basically the same list. It had different stars. I think they've expanded it, but in 2017 it was still M dwarf stars. If you go to the RTB website, you'll see there's a gazillion papers about that's like the worst place to look for Earth-like planets, is M dwarf stars. So so there's just a lot that goes into habitability. So I mean, like in conclusion, I would just say, let me just say this one real quick here. Pay attention to the news. I think it has gotten better in the last 7 or 8 years as far as saying goofy things like, hey, Earth 2.0, because people are really starting to see that there's a lot of stuff baked into that. You don't see so much overstatement anymore, but it does happen. We're still, even though we're up to 5,800 planets, I mean there's so many more, and we're expecting a lot from James Webb. Habitable zone means a lot more than just liquid water. There's at least 9, maybe 10. There's probably a lot more. I think it's one of those fields, like the more we dig into it, we're going to find a lot more special conditions. And then from a Christian perspective, I'm not sure You know, we shouldn't be discouraged by that, right? We can use that. You know, we see a lot of you know, the God of the Bible talks about purpose and design, and so the question is, if that's all true, should we see design out there? And many people seem to think that, as like what Carl Sagan once said, that Earth, from the Pale Blue Dot speech, that Earth's in a distant void in the galaxy. No one's here to, we're not special, and so forth, right? Well, it's actually the opposite of that. We're not finding anything that looks close to like Earth, and so that makes some people
Sorry, we
wonder.
lost a couple of words due to the internet connection. Could you just go back out one sentence? What Carl Sagan had said?
Oh, yeah. I was just saying, I was trying to rush it here a little bit, but
Darn.
if you guys are familiar with the Pale Blue
Paused
Dot
again.
speech, can you hear me? The
think it's
Pale
all
Blue
right.
Dot speech from Carl Sagan.
Yeah, come-
I'm just saying he painted a picture back in the 1980s. When they took that camera from Voyager as it passed Saturn, they looked at Earth and it said, "Hey, look, that's the only home we know of. We're in a very distant port in the galaxy. We're all by ourselves. There's nothing unique about the Earth," and so forth. So this is just the tip of the iceberg, right? The more we study exoplanet research, we're actually finding how unique Earth is. And so I think, as from a Christian perspective, right, we see that as fine tuning and God's grand design, right, in order to have a relationship and host an advanced life on a planet like Earth. And so I think for Christians, we agree with all these things, and we should expect to find more and more difficulties that that life like a planet like Earth's not really prevalent in the galaxy. And so this presentation I'm showing you guys today is just really the tip of the iceberg. I have a follow-on one where we look at galactic level habitability, and so maybe we can talk about that some other time. But I think I'll end there. I encourage you to go look at those databases and just know that habitability is very complex, and there's a lot of features that need to be understood. That's all I'll have. I can take any more questions.
Well, I have a question.
Sure.
Yeah, I assume when we talk about habitability that we're talking about carbon-based life. I know some years ago they tried to say that silicone might have been a way that you could have life, but that's been pretty well.
Yeah.
Okay. So if we're
Yeah, that's
talking
true.
about strictly carbon-based,
Yeah, I
now,
mean that's in fact, like as you said, if you go to those paper, there's good reasons why you can't have silicon based life, but there's honestly, there's no other way we know of life because carbon is so abundant, and um it's embedded in all life's like amino acid chemicals and DNA and so forth. So yeah, I mean, I guess you could say, hey, there could be some other form of life, but that's just speculation at this point. But yeah, I
okay,
think most people would agree that all life, like when you look at the basic chemicals needed for any kind of life on Earth, organics, right? They're looking for organics on like asteroids and comets, right? They're all carbon based.
yeah.
So yeah,
Okay, well, the other question I had was one, it's simply this, that is it possible when we talk about habitable planet, is it possible to have a planet that is habitable in half of it or part of it, and you could have advanced carbon-based life, and the other part of the planet is not habitable? In other words,
yeah,
okay, so it isn't that the whole planet has to be habitable
yeah,
for life to exist. Is that right?
yeah. Yeah, I think. I mean, that's a serious possibility that needs to be studied. On the tidally locked planets, um, most people are, well, okay, I would say the community is divided on that. Most people think no, but there is a large body of folks that say, hey, I'm going to look on the Terminator side, right at the Terminator, right? You're right at that sweet spot from day to light. There may be conditions that could be suitable for life. But then what complicates that is if life takes billions of years, right, for that to be stable, right? You have to have stability too, and that's the problem with all these other habitable zones is how do you have that maintained over the life of the time it takes to require to develop the life too. So yeah, I mean, nothing's not, I mean, it's not like it's impossible, but that's a difficult situation, but there are people looking at it. That could happen.
Okay. Well, one thing that I've noticed, in particularly in the last 100 years, that we are globally dependent for survival.
Mhm.
And I'm curious, how could you have a planet that's only partly habitable and have advanced life forms that can live within that restricted zone? Because we're having
Yeah.
a hard time living on this planet when we
Yeah.
have the whole planet.
You're right. Yeah, I agree. I mean, those are definitely challenges. I I don't we don't have an answer for that, right? I mean that
Mm.
we don't know, right? We're just barely identifying planets to begin with. But if you notice, I didn't talk about plate tectonics. I didn't talk about the carbonate silicate process. I didn't talk about the magnetic fields, right, of the Earth, right? So there's a lot of other things that need to be in place that would help influence that. But you're right. It is a global ecosystem, right, that has to
Yeah.
be kind of taken into account. And it's over long periods of time too. So that you're right, that adds a lot of complication.
Yeah. Okay. Thank you.
Good thoughts, yeah.
Thank you. This has been a great presentation. I appreciate it.
Okay. I know there's a lot of information. It was really meant to be sort of a resource, and I wanted to give you the papers. On the last page, I have, oops, these are all the papers I pulled that from. And so you could read Hugh Ross's book where he kind of summarizes it, but all the details are in these papers. And so um, I would just say some of these, the authors acknowledge these as being problems, but in some cases, I'm trying to remember which one, but there's one of these, the author thinks it might actually, it's the fast rotating one. Like if you go back to this, let me go here real quick. Yeah, this one. You could take the flip side of this argument and say, hey, for a lot of the planets that we know are closer in, if they're actually rotating a lot faster, right, they're going to be pushed further out. Well, maybe they are into that quote unquote habitable zone now. So those are trade-offs. So those yet to be seen because we don't know anything about planetary exoplanet rotation rates yet.
Go ahead, Tim.
So as far as planets that are partially habitable, I think we don't understand enough necessarily about habitability zones at this point, but it seems that this planet is a good example that's partially habitable. I mean, we don't see natives dancing around in Antarctica, and that's
Yeah,
because
yeah,
we've
that's
got
true.
some of the habitability
Yeah.
zone studies that we haven't delved into. But my other
Yeah.
question
Yeah.
was a while back, I read something Hugh Ross said about only G type stars would support life. Has that been expanded now?
So that was Hugh Ross's opinion, but it's based on a lot of this data, right? Because the problem is if when we go to like hopefully you're saying this, but we're pretty sure indoor stars are going to be the most challenging for a whole host of reasons. So G stars are only 7% of the stars. K stars are kind of close, they're in between. So, but the problem you have there is look at their masses. They're like kind of half the size of the sun, right? These are very cool stars. So you're kind of like it's sort of like a mixed bag of all these potential problems that I kind of was talking about today. So that's not to say that there couldn't be some around them, but if you know, if some of those K stars could meet some of those qualifications, right? It's only a few more percent above and beyond what the G stars are, right? If it's a portion of these. So there, I mean, I don't think even Hugh Ross, I don't think anyone really knows the answer at that point. But I would say there's potential because if you look on that last, sorry, I'm flipping again here. I'm going to that from the latest database. Right, we have 2 stars, Kepler 442b, number 17. Okay, let's look at it here. It's 2 times the mass of the Earth. It's a little bit smaller in radius. Oh, I'm sorry. It's 1.3 times the radius of the Earth, so it's a little bit bigger. Now look, because it's a K star, remember it's cooler, so it only has 70% of the energy flux relative to our sun. So think about that, right? If it's pretty close to like our Earth, imagine our Earth, but we only have 70% less energy from the sun. Now, the other thing which you're not seeing on this chart here is K stars, and then even in getting cooler with M dwarf, right? You're increasing in ultraviolet outbursts and things like that from the sun, right? From the star. So that's got to be factored in. So, and then, yeah, I'm not seeing any. I guess you'd have to kind of go in the database. There's more information here, but this particular planet takes 112 days to orbit around its star, right? And so, but this says nothing about tilt, and I don't think it's tidally locked, but it could be, but I don't think it is. So, yeah, I would just say when you actually go into the spreadsheet and go to the actual data, right, it has all those parameters, and you can start to look to see. I think there's some guidance in some of the RTB articles that help you. You could actually go in and start sorting on those files. And I don't have it in here. I took it out, but on the 2017 data, we had 3,000 something confirmed planets, and I applied all that criteria, and I came up with 2 candidates. And one was a K star candidate. That's just me kind of playing around with the spreadsheet, though. It's possible, though. We're really just beginning this whole idea of exoplanet research. The whole point of this presentation is really to tell you, hey, there's more than just liquid water to consider, right? For habitability, there's all sorts of things that you need to look at. And on top of that, not every star, like they're making it out to sound, can probably host life. A lot of them have a lot of big problems. Most of them do.
Is it safe to say that there's no Earth-like planet around an M-class star?
No, because they if you
No, I
let me
meant
go
it.
back. Yeah, let me go back here for a second. Sorry, I pulled it off the slideshow. So for instance, look at number
Yeah.
A
1,
good example.
right? Now, when you say Earth-like
was
planet,
197.
what do we mean, right? That's a matter of definition. A lot of these guys look at this Earth
A
similarity
life
index.
candidate.
Yeah. So for instance, like this one, this star is 8 billion years old, but it's an M dwarf, so it's going to live a lot longer. So I don't know relative. I'd have to go look at the star to kind of estimate its lifetime, but relative. So in other words, if it needs billions of years for life to develop, you don't want that process to start too late in the star's life cycle because then it's not going to make it to the end. Or stars get brighter as they grow older, so that adds complications. Right. So there's just so many features you got to think about.
Okay, thank you.
Ryan, another
Yes.
question.
I just have a question about surviving in space. I mean, are we actually going to be able to make it to Mars and back without serious medical issues from the hard radiation of space?
Yeah.
Ryan, we have an internet.
Yeah, they can
connection
do
right
it.
now.
The trick's to get there faster. Now, obviously we're not, the new direction is to go you know, we don't know what designs, but we're still limited to chemical rockets.
Internet's
But
really bad.
so I think you know we can't shield the GCR, the galactic cosmic radiation, well enough. I mean, people are still going to get absorbed, but it's not like an acute dose where you're going to die instantly. They monitor those things and they factor those in, and the whole goal is to minimize
Okay.
astronauts' doses.
Well, I'm just wondering if anybody. Yeah,
You
but
brought
to
the part
have a
there.
civilization on another planet.
Well, it'll be difficult on Mars because
Yeah,
Mars
the
has no
internet's terrible.
atmosphere, right? I'm not sure if I broke apart. Did you hear
We
that?
lost you.
Do you hear me now?
Oh, could you repeat that? Things breaking up. Yeah. Yes.
Okay, what I was saying is Mars has 1,000 times thinner atmosphere than the Earth. So, were you able to hear that?
You probably should wrap it up.
We're done. It's not,
Yeah,
it's terrible.
I'm sorry, the internet's dropping, but
Okay.
if we don't get to say goodbye any better, thank you very much, Brandon. This was great.
Okay.
So let Julie. do
Oh,
her-
Julie's gonna come up and
Okay.
you hear us?
Yeah, I hear you.
Julie.
Do you hear me?
Thank you. Okay, yeah, it just goes back and forth. Something is losing on the internet.
I would just say, hey, real quick on the Mars thing, Mars has no atmosphere, so we can't shield radiation like we can on the Earth. So that's a problem.
Yeah.
Yeah,
I'm
no
actually
magnetic
su-
field.
I'm really surprised that you seem optimistic that there could be other habitable planets.
No, I'm not. I don't think there is any.
Oh, okay, all right.
I used to be, you know, I'm open to the idea, right? Like, I'm a Christian. Like, you know, God could have created life somewhere else, but honestly, the more I dig into it, the harder I think it is that we'll find anything. So that's just my 2 cents.
Okay, all right. Well, thank you very much for coming. I know we all appreciated your expertise, and hopefully we'll have you back again sometime.
Sure, no problem. I appreciated it. And
Thank you.
Thank you.
And next month, I should say, we are going to have Stephen Willing talking on transgenderism. And what does the science say? So hopefully everybody can come on back. Thank you.
All right, thank you.